Welcome back to Applied Physics Lecture Series, Unit 4 Fiber Optics, Lecture 6 Principle and Structure of an Optical Fiber. So, first of all, you have to know what is meant by fiber optic or optical fiber cable. So, this is the diagram of an optical fiber cable, so which is used for the purpose of communication. Basically, it is used for the transfer of communication signals from one place to other place in the form of light pulses. And how do you define the optical fiber? An optical fiber is a cylindrical waveguide and made up of a transparent dielectric material, usually either it's glass or plastic, and occasionally it is also made up of with silica, and which guides the light waves along its length from one place to other place within a short span of time in the form of total internal reflection. That means the principle behind the propagation of light in an optical fiber takes place in the form of total internal reflection. So how to achieve this total internal reflection, or what are the minimum conditions to fulfill the total internal reflection? So the first condition is light should be passing from denser medium to rarer medium. And second condition is the angle of incidence in the denser medium should be greater than the critical angle of incidence. And if we consider the structure of an optical fiber, basically it is having three coaxial regions named as core region, cladding region, and outer jacket or sheath region. So it is having three coaxial regions, thereby the innermost coaxial region is named as core region. And it is the light guiding region, and always the refractive index of core is represented with N1. The main purpose of this core region is nothing but light is traveled in the core region of the optical fiber by undergoing total internal reflection. The middle coaxial region, which completely covers the core region, is cladding. The purpose of this cladding is it restricts the light. As a result, the light is always present within the core region. At any case or at any stage, so light is not allowed to come out of the core region. That is the purpose of cladding. Here the refractive index of cladding is always represented with N2, and always we have to maintain a condition of N1 is greater than N2. That means the refractive index of core, which is represented with N1, is always greater than the refractive index of cladding, which is represented with N2. Then the outermost coaxial region, which completely covers both the core and the cladding regions, is either sheath, or you may call this one as outer jacket, or sometimes it is also called as buffer jacket. So it is a plastic coating, so which protects the signal from the external contaminations, in addition to provide mechanical strength to the optical fiber. Already I mentioned the principle behind the propagation of light in the core region of the optical fiber is total internal reflection. Now we will see how the total internal reflection will be takes place. So the minimum requirement or the condition light has to satisfy to undergo total internal reflection is theta I must be greater than theta C. That means the angle of incidence must be greater than critical angle of incidence. Now let us see how we will achieve this condition. If we consider a medium one, which is nothing but core region, that is the light traveled region, whose refractive index is represented with N1. And we will consider another medium, which is nothing but cladding medium. The refractive index of cladding is represented with N2. Here we are having three diagrams in the figure A. So see here, theta 1 is less than theta C. Here theta 1 is nothing but angle of incidence in the core region, and it is less than the critical angle of incidence. And we will see the figure B. So here theta 1 is equals to theta C. That means the angle of incidence in the core region is exactly equals to the critical angle of incidence. So how it is achieved? So for which angle of incidence? The angle of refraction is exactly equals to 90 degrees. In that case, the angle of incidence itself becomes critical angle of incidence. Here theta 1 is the angle of incidence in the core medium, and theta 2 is the angle of refraction in the cladding medium. Observe here, the angle of refraction in the cladding medium is exactly 90 degrees. That's why the critical angle of incidence is equals to angle of incidence. But in both the cases, total internal reflection is not possible. In order to achieve the total internal reflection, theta I must be greater than theta C. How to achieve this condition? For which angle of incidence? The angle of refraction is greater than 90 degrees. In that case, angle of incidence is greater than critical angle of incidence. Thereby, total internal reflection is possible. So that case we can able to see in the figure C. Observe here, theta 1 is the angle of incidence in the core medium, and theta 2 is the angle of refraction in the same medium. That means here angle of refraction is greater than 90. That's how you can able to see theta I as greater than theta C. That's why you can observe the light is completely reflected back into the same medium. That means total internal reflection takes place. So we will observe how exactly the total internal reflection takes place in the core region of the optical fiber in this diagram. So the propagation of light in an optical fiber is based on the principle of total internal reflection. Here you have to satisfy two basic requirements. One is the refractive index of core material, which is represented with N1, must be greater than the refractive index of cladding, which is represented with N2. This is the minimum and mandatory requirement. And second one is, at the end of core cladding interface, the angle of incidence theta must be greater than critical angle of incidence theta C. In that case only, the light which is entered into the core region of the optical fiber is completely reflected back. Once it is reflected back, it will undergo successive multiple total internal reflections. As a result, light will be traveled from one end of the core region to other end of a core region in a zigzag path over the length of the fiber within a short span of time. And whenever we are considering two refractive indices, that means if you consider the two different mediums of refractive indices, so how to apply Snell's law. So what is Snell's law? The ratio of sine of angle of incidence to the angle of refraction is the ratio of refractive indices. Sine of angle of incidence to the angle of refraction is the ratio of refractive indices. Observe here, in the short form, it can be written as n1 sine theta 1 equals to n2 sine theta 2 in this particular case. Observe bottom in the light pink color, that is the core region of refractive index n1. Top white color, so which is co-cladding region of refractive index n2. Light is entered into the core region, so by making angle of incidence theta 1. It is refracted, it bends away from the normal, so by making refraction angle as theta 2. So when theta 1 is equals to theta 2, theta C, that means angle of refraction is exactly 90 degrees. In that case, total internal reflection is possible, not possible. But if you observe, if the angle of incidence is theta 1 and theta 2 is the angle of refraction, which is greater than 90 or exactly equals to 90, in that case, theta 1 is equals to theta C. Therefore, n1 sin theta C equals to n2 sin 90 degrees. Sin 90 is 1. That's why sin theta C is equals to n2 by n1. Here, theta C is nothing but critical angle. These are the basic parameters related to the structure of an optical fiber as well as the principle behind the propagation of light in case of optical fiber, that is total internal reflection, and we discussed all the conditions. That is how we are achieving total internal reflection in the core region of the optical fiber. Thanks for watching.